Okay, lesson number 5 for differentiation. Now we have been looking at differentiation in terms of gradient. So we've been looking at it as a way to calculate the gradient at any given point on a curve, because we know that the gradient varies across the curve. So when we differentiate a function, we find an expression that describes the gradient at any given point on a curve. Now this first tangent that I've drawn in here, it shows us the gradient at this point here. It's a positive gradient and it's sloping quite slowly in that direction. The other tangent that I've put in here shows a negative gradient, but it's much steeper. It's going down much more quickly. Another way to describe the derivative is the rate of change. So what we are calculating here is how quickly the curve changes. We've worked out how to make an expression for that gradient, that rate of change. What we're going to look at now is, well, exactly what's happening at this point here. So I've worked out an expression for describing this point, but what I want to know now is, what's the actual number? What is the rate of change at this given value on the curve? What's the rate of change over here? And what's the rate of change over here? I want to be able to get a value for that. Before we go any further with this, we're just going to do a little quick reminder of some of our indus work. Now, we've worked on this already. X to the power of 4/3 is the same as the cube root of x to the power of 4. And that's because the 3 tells us the order of the root, the 4 tells us the order of the power. Now, if this is not actually x and it's a number and we want to evaluate it, we use exactly the same rules. So if I had 27 to the power of 4/3, it's the same as the cube root of 27 to the power of 4. Now, if I'm going to evaluate this, I can choose the order. So I can either take the cube root of 27 and then raise that to the power of 4, or I can work out 27 to the power of 4 and work out the cube root of that. Now, it's going to be much easier to take the cube root first, because I'm going to get a smaller number that I can deal with. And I know that this is a whole number, because the cube root of 27 is 3, because 3 times 3 times 3 is 27. So that means I've worked out the cube root of 27 to be 3, and now I need to raise that to the power of 4. Well, 3 times 3 times 3 is 27, times 3 is 81. If you are not confident in this skill, please go to the essential skills at the back and practice this before you attempt the exercises today. Okay, so we're going to go on page 7, and we start off with example 1. F of x is 2x to the power of 5, and we're asked to find the rate of change when x is equal to 3. So the first thing we're going to do is we're going to find the expression for the rate of change, which is the derivative. Multiply by the power, reduce the power by 1. We have 10x to the power of 4. Now I want to know the rate of change exactly at the point when x is equal to 3. So instead of f dashed x, I want to know what's f dashed 3. And I'm just substituting 3 in to x at this point. So 10 times x to the power of 4 becomes 10 times 3 to the power of 4. Now 3 to the power of 4 is 81. We worked that out in the example earlier. Multiply that by 10, 810. So the rate of change at the specific point where x equals 3 is 810. Okay, 2. This time y is equal to 1 over x to the power of 2/3. Now before we differentiate that, we're going to have to do a bit of preparation. The x is on the bottom of the fraction, so I want to bring it up, which makes it negative. So it's going to be x to the power of negative 2/3. I'm going to differentiate it using Leibniz notation because I've been given y. So dy by dx is equal to multiply by the power negative 2/3, reduce the power by 1. It's going to be negative 5/3. Now before I can substitute in here, I'm going to need to tidy this up. So that means I need to get rid of negative and fractional indices. So the negative index here tells me that I need this x to go underneath the fraction to make that positive. The fraction, the 3, tells me that the root is order 3 and 5 is the power. So this is the same as negative 2 over 3 times the cube root of x to the power of 5. Okay, I'm just going to continue this on the next. So now I want to know, we've worked out an expression for the rate of change or the gradient, and now I want to know specifically what is the rate of change when x is equal to 8. So we're just going to substitute 8 into here. So I've got negative 2 over 3 times the cube root of 8 to the power of 5. Now when you're evaluating something like this, you've got to remember your order of operations, the bid mass. So we're going to straight down to here and we're going to be evaluating this first. Now again, I can choose to do the cube root of 8 and raise that to the power of 5, or I can do 8 to the power of 5 and take the cube root. Cube root of 8 is 2, so I'm going to go straight ahead and say 2 to the power of 5. I'll just substitute that in, so I've got negative 2 over 3 times 2 to the power of 5. 2 to the power of 5 is 32, and if I multiply by 3, that's 96. So that's equal to negative 2 over 96, and I can simplify that to negative 1 over 48. So the rate of change at exactly the point when x is equal to 8 is negative 1 over 48. Okay, just answer these questions in your jotter. When you're asked for the rate of change, what steps would you expect to take? There's 2 things you should be expecting to do. Number 2, can you find the rate of change of y when x is equal to 2, given that y equals 6x squared minus 7x? Okay, and now we are ready for exercise 6e. Question 1 to 4. Our unit level. And question 5 and 6 are level C.